Okay, hello. I'm gonna show you how to use scientific notation and significant figures. Usually in your chemistry and physics classes, you'll be using these. Okay, so with scientific notation, I'm gonna show you like an example of when you would use it. So, for example, say that you had a number like this, or say that you had like a number like this. This one's like a very big number, and this one's a very, very small number, and it's kind of tedious if you want to like represent your number like that, especially if you're plugging into your computer or if you're like showing it as your final answer. You kind of want to make it into a simplified form, right? And so this is why scientific notation comes in handy. So I'll explain how to like change this number into a scientific notation. Okay, so here if you look at this number, it has 6 zeros, right? So we're gonna make it so that the number only has actual numbers. So, before that, actually, I'm gonna show you what this equation is. So basically, scientific notation is gonna be a number times 10 to the power of something. And then this a value right here, has to be like this. So basically, it has to be greater than or equal to 1, but less than 10. And the reason it's less than 10 is because if it's greater than 10, you can actually put it into the exponent. We're trying to make it the most simplified possible. Okay, so here, the decimal is here right now, and you want to move it up to where the number that's left over is, again, greater than 1 but less than 10. So if we move it here, this whole number is greater than 10, so that can't be possible. If we move it here, it's still greater than 10, which can't be possible. And then if we move it here, though, it's greater than 1, but less than 10, so that's perfect. So now we can count how many times that you have to move to the left. So 1, 2, 3, 4, 5, 6, 7, 8. 8, okay? Remember that? And then now what you're going to do is it's going to be 2.56, right? Then if you look at the format, it's times 10. Always going to be times 10, not like 1,000 or anything. It's always going to be 10. And then n, and n is actually going to be this value right here, which is 8. And then that is this number in scientific notation. See how this n value, or this exponent right here, is a positive value? What you basically did was you made this huge number small so that it can fit into the scientific notation. But when you're making the scientific notation, like you're expanding it, you're trying to make it bigger, right? So because it's getting bigger, the exponent actually should be positive. Okay, and then we're going to do the small one. So I'm going to show this a different way. Basically here, I'm going to kind of work backwards. You can work either way. So basically, what your a value is going to be is, okay, you want your number to be greater than 1 but less than 10. So it's probably just going to be 6, right? Usually, when you're writing in scientific notation, you always like to have a decimal with a 0, especially if it's like a 1-digit number. So 6.0, and then it's going to be times 10 to something, right? So now we can figure out what that something is. So our decimal right here is here, and we want to bring the decimal all the way here, right? Because you said 6.0. So you want to bring it 1, 2, 3, 4, 5, 6, 7, 8, 9 times. And because you're making the number bigger, but you want to make it smaller, when you expand the scientific notation, it's going to be a negative number. So negative 9. Should have wrote that in red, but okay, yeah. And then also, if you're moving your decimal place to the left, the exponent's going to be positive. And then if you're moving to the right, the exponent is going to be negative. And that's basically what scientific notation is. You're just condensing a really large number or a really small number. Or you're basically saving the zeros. You're just condensing them. So it's easier to type into a calculator and to like present your work. And just saying it in general is also a lot easier. For example, if this was the amount of seconds, instead of saying whatever this huge number is, you can just say that it is 6.0 times 10 to the negative 9 seconds. Yeah, that's basically scientific notation. And now I'll do significant figures. Or in short form, they're actually called sig figs. And there's multiple like steps to this. So basically the first one would be any numbers, so any actual numbers that are not 0. So here. So for example, if you had like 56, there's no zeros here, so there is 2 significant digits. So okay, and this basically works with decimals, any numbers. And then your second one would be if there's zeros placed in between like 2 numbers. Okay, so for example, if you had like, I'm just gonna use the same example. So if you had like 5,006, these zeros like count as significant. So we already know that 5 and 6 are significant, and these two are also significant. It's like a sandwich, so everything in between the sandwich is gonna be significant. So 4 significance here. Okay, and then now your third rule is basically if you have a decimal number that is like really small, like all zeros before a number shows up, all of those zeros actually do not count as significant. And in like chemistry, physics, these are called leading zeros. Okay, so again, do an example. So basically, this rule is basically only for numbers that are really, really small. So if you had like 0.00056, these are called leading zeros. And then these two will be significant. So 2 sig figs. Okay, so far I think it's pretty simple. And then if you have in a number that's like no decimals, all the numbers that are zeros don't count. So here. And these are the ones that are called trailing zeros. So for example, if we had 5, 6, 0, 0, these are called the trailing zeros because there's no decimal point and they end with zeros, so these are called trailing zeros. And so the only numbers that are significant are the numbers that are not zeros. So 56, so 2 sig figs. Okay. Then there's a lot of rules. 5 is basically if you have a decimal point and the numbers after a number that is significant, all the zeros are significant. I'm going to show you an example, okay? So, for example, if you had 0. I'm literally using the same numbers over and over again. 0.056600. First of all, like we said, these are actually called leading zeros, so they don't count. Do not count. And then these ones, because it's after the decimal and after a number that is significant, they are significant. So 1, 2, 3, 4. Okay, and then your final, I guess, rule. Not really a rule, I guess, but if you have like a number in scientific notation, all of the digits are significant. So for example, if you had 5.6000, if this wasn't in scientific notation, it's still gonna be, everything is gonna be significant because first of all, it's a decimal number, and these zeros are after a decimal and a significant number. But yeah, it's like times 10 to the 3. All of these are significant. And that is 1, 2, 3, 4, 5. And then in general, if you have a number that's 5.0, there's 2 sig figs because it's after a decimal and there's a number before it that's significant. Okay, I'm gonna like summarize this in a way where you don't have to really memorize these rules because it's a lot. Basically, how I think about it, I'll show you. So say I'm not gonna use these numbers anymore. So say that you have 300.0056. First of all of these are gonna be significant because these zeros are sandwiched. So, and same with the zeros, all of them are significant. If I have a number that's really, really small, like this, I already know that these are the only ones because they're literally covered with zeros. And then if I have like 5,600 with no decimal, only these two are significant because these are the trailing zeros. And then if you do have a decimal, that changes the rules. So all the zeros after the decimal are significant. That's it. You kind of just need to memorize like how the decimals work and if they're sandwiched or not. Here, I'll do like a few examples quickly. So if you had 0.0041, again, these are called leading zeros, so they're insignificant, so they're not significant. So this would actually be 2. If you had 2.040, so this is after the decimal and this is sandwiched. So everything is significant here, so 4. If you have 10.0, basically, I guess anything that has a decimal and there's a number before it, everything is significant. So this is 3 sig figs. Okay, I'm going to go back to what I was saying before. So with scientific notation, you basically add this 0 based on how many sig figs there is. So for example, if in the question you only needed 1 sig fig, this would actually just be 6 times 10 to the negative 9. Whereas if you needed 3, you would just add another 0. That's how scientific notation kind of helps with the number of sig figs. I'm gonna now show you how to do like calculations with significant figures, because multiplying and dividing have different rules than addition and subtraction. Okay, so when you're I'm just gonna show the sign. Okay. When you're doing multiplication and division, basically the amount of significant numbers, digits that you use in your final answer is based on the number that has the least amount of significant figures. So for example, if you had 77.8 times 0.89 67. Basically, you would count the significant figures. So here, you actually have 4, and then here you actually have 3, right? So then now you do your calculation. So 1 second. In your calculator, what you would get is 69.76326, and because I said earlier, like, you use the smallest amount of significant digits, so 3, you would have to round your number so that it only has 3 significant figures. So in this case, 69.8 would be the answer. I'm going to do one more example. So if you had 638 times, so say you had this, this has 3 sig figs, this only has 1. So if you multiply this, you already know that it's going to be 3800. But because this has 1 sig fig, you have to round the whole answer so that it has 1 sig fig. So this would literally be 60,000. It kind of doesn't make sense sometimes, but yeah, this would be your final answer. Basically, you base it off of the number with the lowest amount of sig figs. And the same thing with division. So say instead of multiplication, if this was division, you would have 6.38, but because there's only 1 sig fig here, you would have to round it so that it's only 1 sig fig. So 6 would be the final answer here. Okay, I'm sorry, this video is very long. Okay, if you have, okay, when you're adding and subtracting now, so, like this, okay, when you're adding and subtracting, the rules are kind of different. So an example, it's easier. So say you have 0.003 plus 1.224. It doesn't really matter how many significant numbers you have. You're basically just seeing like how precise a number is. So for example, both of these actually have like 3 numbers after the decimal. So with your answer, that's what you're gonna have. So the answer is 1.227. Okay, that one's pretty simple. And then if you have a harder example, so if you had 75.5 subtract 22, you can actually see that this number right here has a number after the decimal place and this one doesn't. So you're going to use the one that's least precise. So you can actually have a number that only holds 2 place values. So this would actually be 54. And you round down or up based on what your value is. Okay, I'm going to do a even harder example, and this is going to be the last example. Okay, so if you had 23.9871 minus 0.00234. Okay, so you can see that this actually has 4 place values. This has 5. So you're going to use the one that's least. So you're going to try and have 4 place values. Answer would be 23.9848. But yeah, that's you basically just follow the place value of the number. And that's how you do scientific notation, and that's how you use significant figures. Thank you.